And here we are, the last topic that we will cover in fluids. I will pause for a minute so you guys can finish cheering. Okay, let's take a look at things. We're going to talk about that last composite force, lift. This is the force that actually allows things to fly. This is where we get the term lifting body. And basically, whenever I say lifting body, I'm talking about anything that generates a lift, which is typically your airfoils, your hydrofoils. Sometimes the body of a plane or the body of the ship itself can provide lift, and so it would be a lifting body. Now, for ships, this is not to be confused with buoyancy. Buoyancy lifts the ship up just by the nature of the differences in density compared to the fluid that it's in. A lifting body would be something that actually generates lift, which means it generates it via motion. So let's take a look at our airfoil and just a couple of key terms that we need to think about. And that is a couple of these we've already talked about. The chord, which is the distance from the leading edge to the trailing edge. The thickness is basically the bottom to the top surface at any point. The span would be the wingspan. The last thing, the kind of new thing for us here, is this alpha. And alpha, when we're using aerodynamics, would be the angle of attack. And the angle of attack would be how much the wing, the lifting body, is tilted in relation to the free stream velocity. So if my angle of attack is 0, my airfoil would be pointed directly in line with the velocity. If I have an angle of attack of about 15 degrees, that means that I am angled 15 degrees off of my velocity. And that will come into play for how we generate lift. One second, I need to get us some more space. So to calculate out lift, it's actually a lot of the same stuff as drag in the simplified version that we're going to be looking at. I just noticed my pen's black. But we're going to have a coefficient of lift. It's going to be equal to the lift force divided by rho over 2 v squared AP, where AP is what we call the planform area. Now, unlike drag, we only have one area to worry about because we need that planform area to generate the lift. And that planform area is B times C, the span times the chord. It's a projection of force, much like our frontal area, except we're looking down on the top. Now, coefficient of lift, it's a function of a lot of things. The big ones being shape. Once again, Reynolds number, Mach number, Froude number, epsilon over L, and alpha. So the difference for this one is really the inclusion of alpha, and we'll talk about that here in a second. Froude number, once again, only is going to matter for underwater wings. We do have epsilon over L here, but really the surface roughness is mostly unimportant because it's mostly going to be influencing drag. So most lift-generating bodies are going to operate in a high Reynolds number region where there are boundary layer and wake effects. And once again, if we take a look at way back when we first were talking about these composite forces, you have your shear forces along the wing, and then you had your pressure forces, pushing up, and then negative pressure forces on the top. Shear forces are mostly going to be all about drag. Pressure forces are really going to drive what's going on with the airfoil. Now, looking at that, one thing to keep in mind as we talk about lift is all of our lift theory is consistent with Bernoulli's theory. So I will be talking about lift, basically talking in terms of Bernoulli's. This is a very simplified way of looking at lift. Bernoulli's theory does not cause lift. It's not the reason for lift. It's just our theory is consistent with the lift. There's a lot of things going on with lift, dealing with the boundary layer, circulation around the wing, and a bunch of other stuff that we're not going to go into in the context of this class. We're keeping it very light and just talking a little bit about what's going on. And the reason I bring this up is if you go online and look at something, and you'll see arguments about lift theory has nothing to do with Bernoulli's, but yeah, it does. It's consistent with it, but it does not drive it. So we'll talk in terms of that. Now you will see airfoils a lot because they generate lift. You'll see them on planes. You'll see them on hydrofoils. One place that I do like to just quickly, as an aside, talk about, one of the fascinating places that you'll see an airfoil is on a Formula One race car. As I said before, the Formula One race cars are amazing with the way they're put together because there's so many things going on. Formula One race cars travel so fast that their bodies are lifting bodies. The body of the car will generate lift. Now, this is a bad thing because if you have your little Formula One car and it starts to generate lift, what does it do? It starts to skip off the road. You need those wheels to be in contact with the road to be able to keep going. As if you're jumping up in the air and losing contact, because, I mean, it's not enough lift for it to take off for flight, but it is enough to pull it off the road. And so that's bad because it'll slow it down. So what do? Is you have your spoilers that they put on the car. What are spoilers? Spoilers are inverted airfoils. So they are generating lift in the downward direction. And this is where it's fascinating because they spend a lot of engineering time calculating out. We're going to be traveling at the speed. They want to generate just enough lift to push the car down on the ground to keep the tires in contact with the road, but you don't want it to be too much, because if it's too much, you're pushing down on things and you're slowing the car down. If it's not enough, the car's going to skip on the road and it's going to slow down. So it's a really cool thing. It's not like the little carrying handles that you see people put on the back of their cars where they have these huge spoilers that do nothing. But on like Formula One race cars, it's a highly, highly specialized technical kind of thing. Okay, so let's go and talk about airfoils and that whole idea of being consistent with Bernoulli's theory. So let's look at, what we're going to look at is what's called a symmetrical airfoil. Symmetrical airfoil means that everything above and below the chord line is symmetrical. So now as I look at a symmetrical airfoil, and once again with this eye of that we're consistent with Bernoulli's theory, if I have a streamline that comes in, hits the front, and it splits in two, the top and the bottom have to travel at the exact same speed to meet up again at the end. And so what does that mean? Since lift is really going to be based on this pressure distribution, and if I think about Bernoulli's theory, that if the pressure goes up, the velocity goes down. If the velocity goes up, the pressure goes down. If I'm traveling on a streamline and they're both the same, top and bottom, I will have no lift because the pressures will be equalized and lift is really going to be driven by that pressure difference. So does that mean that symmetrical airfoils don't work? Well, no, that's not true. There's a lot of symmetrical airfoils out there. So what we end up doing is we increase the angle of attack. Now, how do we do this? Well, we either tilt the wings themselves or we tip up the nose of the airplane. Typically, if you have a symmetric airfoil on a plane, they will be tipped at an angle of 3, 4, 5 degrees, and then you can nose up the plane to increase the angle more. So now what happens? Well, the Bernoulli's, the streamline comes in and it splits into two lines. The line on the top is longer than the line at the bottom. But the two little molecules that meet here, well, they've got stuff to do. They want to meet here at the same time. So what that forces is across the top of the wing, the velocity has to increase. The guy on the bottom can take his time because he's in no hurry. But the one on the top has to increase. So what happens? Well, that decreases the pressure on the top of the wing. And so now I have a pressure imbalance. It's greater on the bottom than it is on the top. And that causes lift. That causes the airfoil to ascend. So why don't we have just, oh, that's great. Why don't we just keep increasing the angle of attack to get more and more lift. Well, that's when we get into a slight problem, because if we increase the angle of attack too much, the wing will stall. Now, I know usually we talk about stall in context of engines, but when we're talking about stalling in aerodynamics, what we're talking about is the lift generating body is no longer a lift generating body. So what happens is I take a look at this, and this is just a picture of smoke lines, we've increased the angle of attack so much that the boundary layer on the upper surface separates. And you might have remembered when I said, when we were talking about boundary layer theory, boundary layers are very important, because without the boundary layer, we're not going to have lift. And so what happens is that boundary layer rips off, it's no longer a lift generating body, the lift drops off rapidly, the drag increases dramatically, makes the wing unflyable. If you ever go to an air show when they have those aerobatic biplanes and they go straight up in the air and they fall out of the sky, this is what they're doing. They're purposely stalling their wing. There are other ways to do this, to rip the boundary layer off besides just angle of attack. This is one way. This is why planes have to, especially smaller planes taking off after bigger planes, have to wait for the wind to die down, because, or the turbulence from the plane in front of them to die down, because that turbulence can rip the boundary layer off the wing, and it will no longer be a lift generating body. One of the greatest 80s movies ever made, Top Gun, that's how a goose died, is because they got in the wash of the other plane, it ripped the boundary layer off. But anyway, so we can't increase the angle of attack too much, because we will rip off the boundary layer. So is that it? That's the only ways that we take a symmetric airfoil and we have to angle it and tack it up? Well, no. We can also have what's called a cambered airfoil. And that's a non-symmetrical airfoil. It's fatter on the top than it is on the bottom. And it gives us the same effect of tipping up the wing at the angle of attack. Streamline comes in, it takes it longer to go over the top than it does over the bottom. We have a drop in pressure on the top, a higher pressure on the bottom. In balance, it takes off. You can still put this into an angle of attack, increase the lift force, and you can still stall the wing. And so that is how it's consistent with Bernoulli's theory. A couple of last points. If you have level flight, we have our coefficient of lift is equal to the lift force divided by rho over 2 a planform v squared. If I want a level flight, which just means I stay at the same height, my lift force has to equal my weight to keep it up in the air. If my lift force is greater than my weight, I ascend, I go up. If my lift force is less than my weight, I descend, I go down. And just a couple of random things. You want the longer wings you have are more efficient. They have less wingtip losses, which is, if I look at the front of the wing, that's the air going over here, and which is why planes will have those little winglets coming up, but that's beyond the scope of the class. They have low wingtip losses. It's a wind drag that's called the induced drag. Long wings have a lot of inertia. And you think about moment of inertia. If you've got a lot of inertia, it's hard to move that around. So long wings have very bad maneuverability, which means they're very stable. So in a commercial jet, you want something that's really stable, because you don't want it to be moving around a lot. If you look at a fighter jets have really short wings. And so they have less inertia. And they're really short because you want them to be highly maneuverable, and they're what we call aerodynamically unstable. So for a fighter jet, you want the most unstable thing that you can have. Now, instability doesn't mean that it's really, shaking around and stuff, but aerodynamically unstable means that it can quickly change its position. And it will not restore itself. And that is the last topic that we have for fluid mechanics. Just a couple of example problems to show off this, and then we're good to go.